All right, so today we are taking a quick look at Newton's second and third laws of motion. If you remember, we looked at Newton's first law of motion last week, and essentially that is otherwise known as Newton's law of inertia, which says that objects that are in motion tend to remain in motion, and objects that are at rest tend to remain at rest. And so these next two laws that we're talking about pretty much expand on Newton's ideas of motion. So first, let's take a look at Newton's second law of motion, otherwise known as the law of force and acceleration. Now, this second law is more math-based, where the first law is more what we call qualitative-based. So what this law means is it means that the force of a moving object is dependent on its mass and how fast the object is moving. And it also means that the bigger the object, the more force needed to cause acceleration of the object, which makes a lot of sense because in Newton's first law, he talks about the idea of inertia, and that inertia is very much based on the mass of an object. So the bigger an object, the more mass that it has, so the more inertia that it has, which means it's going to take us a lot more force to accelerate or move that object. So when we're using Newton's second law, we calculate force with something called, we call it a force triangle. So one of the things I'm going to ask you to do today, I'm going to ask you to go ahead and figure out how to calculate the force of an object using this triangle. So the way this little triangle works is that if we're trying to find the force of something, what we do is we use our triangle. We basically cover up this, and then we multiply mass times acceleration. And we can use this if we have to find other variables, like if we have to find acceleration, we would cover that up, and then it becomes force divided by mass. So here, let me show you a quick example of how to use the triangle or how to calculate force if you're given mass and acceleration.
All right, we are going to go ahead and do our very first force problem. Let's go ahead and take a closer look at the problem. You give a shopping cart a shove down the aisle. The cart is full of groceries and has a mass of 18 kilograms. The cart accelerates at a rate of 3.25 meters per second. How much force did you exert on the cart? Please round to three significant figures, and please note the unit for force is the Newton. All right, well, first let's go ahead and get our formula down. Our formula is force equals mass times acceleration. Let's go ahead and pull this information from the problem. To start with, your shopping cart has a mass of 18 kilograms because that's your cart and your groceries inside it. The acceleration is 3.25 meters per second. Now if we go ahead over here and set up our formula, we have force equals mass, which is 18 kilograms, times acceleration, which is 3.25 meters per second. So that's how your problem should look with all the information in it. Now let's go ahead and calculate those numbers. Force equals 18 times 3.25, which is 58.5. Now remember, our problem says we have to have three significant figures. So let's take a look. Looks to me like we do. We have 58.5. That looks like three significant figures. And our unit has to be the Newton. Now, we don't always have to completely write out the word Newton. If we want to, we could say that force equals 58.5 capital N. That capital N stands for Newton. So there you go. The force exerted on the shopping cart would then be 58.5 newtons of force.
Okay, and so that's how you calculate the force if we are given the mass and the acceleration. Now here's a problem for you to try. It says a golf ball, which is 0.2 kilograms, is hit and accelerates at a rate of 20.0 meters per second. What amount of force was exerted on the ball? The unit for force is newtons, and please round to three significant figures. So again, what I'd like you to do is just it's someplace in your notebook. This is just a practice problem. See if you can't figure out how to calculate the force for this situation. So what I'd like you to do is I'd like you in your notebook to write the formula that you're going to use. Go ahead and tell me what the mass is. Tell me what the acceleration is. And those are things that you're going to pull right from the problem, and then go ahead and calculate the force. So like I said, you can stop the video at this point and figure that out, and as soon as you're ready, you can start running the video again. So in the meantime, I'm going to go ahead and continue. All right, let's take a quick look at Newton's third law. So Newton's third law says for every action, there is an equal and opposite reaction. And what Newton wanted us to understand was that he wanted to show us that forces always occur in pairs, that you can't have one force acting on an object without another force sort of acting back, so to speak. What he said is that whenever you're putting force on an object, the object itself is actually exerting a force back, which is equal and opposite to the force that you put on it. So let's show you an example. Like here's a great example from the movie WALL-E.
To self-destruct. 10 seconds to self-destruct.
So we haven't quite yet seen the example of Newton's third law, but we will here in just a second.
5, 4, 3, 2.
So here comes WALL-E with his fire extinguisher.
WALL-E!
So right here where WALL-E points the fire extinguisher, fires it, and then is pushed the other way. That's a really fun example of Newton's third law. So that fire extinguisher is exerting a force, and WALL-E's movement is a force being exerted the other way. So that is an example of Newton's third law, at least a cartoon version. Okay, so let's take a look at where we're going with this. Now, just so you understand, at the end of the week, we're going to be doing a little activity that deals specifically with Newton's third law. And you saw last week how I had you take a look at some vector diagrams just so that you could review and familiarize yourself with that, because we're going to be putting those vector diagrams into play with what you see in front of you here. And this is a practice that we did in class today. And what these are called free body or force diagrams. Now, the way these work is that the square represents an object, and here the oval represents an object. The arrows represent forces acting on the object. In here, you see the mass of the object, and the arrow directions are showing us which way the forces are acting on the object. So, for instance, there is a force of 30 newtons that is essentially pushing or pulling this object to the right at 30 newtons. And there is a second force acting on this object that is pulling or pushing it to the left at 10 newtons. So your job, and I would like you to work on the first two. I want you to work on numbers 1 and 2. And what I want you to do is I want you to calculate the net force. And then I want you to, with that information, with the information of the net force and the mass, I want you to calculate the acceleration using the triangle that I showed you earlier. So again, you're trying to calculate the net force using the information here, and then once you've calculated the net force, apply that to the triangle that we showed in the notes that you looked at a little bit earlier. So you're going to do 1 and 2, and then I'd like you to go ahead, and what I'm going to do, I'm going to go ahead and email you this document. So then I would like you to work on numbers 6 and 7, and 6 and 7 are a little bit different. This time you're given the mass of the block, you're given an arrow that shows you the acceleration of the block, and that with that information I'd like you to calculate the force. So like I said, I'm going to go ahead and email this document to you, and again you can just work in your interactive notebook and go ahead and try and calculate these, and then you have a couple of choices. You can share the answer with me via an email, or you can take a picture with a cell phone and share the pictures with me, whatever is easier for you. So again, I'd like you to do problems 1 and 2, give me the net force and acceleration, and then I'd like you to do problems 6 and 7, where you're calculating the force for these blocks if they have an acceleration of a certain number of meters per second. Okay? Look forward to getting this work from you. I hope you're having fun. Bye-bye.